All right, so we have to back up the truck to 100,000 feet. What is a force anyway, right? Everybody has their ideas, but we have to talk about the physics definition of a force. So a force is basically a push or a pull on an object. That's it. We have our own units we talk about in physics. We have our own equations, of course, that deal with forces, but a push or a pull on the object. The one other thing I'll say before I draw on the board is that what does a force do? A force causes a change in the motion of an object. In other words, forces cause what we call acceleration. Now, I'm really harping on this because a lot of people have their own ideas about how forces in motion work, but it's almost always wrong. And as we get into physics here and talk about it in a lot of detail, I'm going to come back to this over and over again. Forces cause an object to change its state of motion. In other words, go from rest to maybe go into a motion state, for instance. Or if it's already moving, maybe when you apply a force to it, it changes its state of motion, either changes its direction of travel, or it speeds up or slows down. Forces cause acceleration. They cause motion to change. So let's jump right in. And first, what we're going to talk about is different types of forces in physics. And then after that, we're going to really get into the nitty-gritty of how to break a force into components, how to add the components, and that is where what I said, the most common question. Hundreds and hundreds of people have gotten confused about adding forces and how to add properly 2 different forces or 3 or 4 different forces in physics. So we're going to clear all of that up now. So what is a force anyway? So let's say we have some generic object here. It's just a box, right? And so if we draw an arrow going into one side, we label it F with a vector bar on top because forces are, they have a strength and also a direction. So it is a vector quantity. And so this would be like a push situation, right? But we can also have a situation with a pull type of situation. So we can have a force that's pulling on an object. We'll call that pull. All right, so very simple, right? Now the issue comes up because when we push or pull things, we don't have to push them horizontally. We don't have to push them vertically, right? You can push them at any angle you want. So instead of drawing the arrow straight like this, I could be angling it up, trying to pull it kind of at an upward motion. Of course, I'll drag it across the ground. If you got to imagine there's some ground here and it has some weight to it or something. Angling a force up or down is going to change exactly the way in which this thing moves. Same thing with the pushing force. Now, why did I talk about in the beginning that a force causes a change in the motion of object? I want you to drill that into your head early on because it's one of the most common misconceptions in all of physics. Because you see, if I take a crate like this box and I put it on the carpet, in our everyday experience, we have to always pull on it to get it to move. We have to continually apply a force onto that crate or whatever it is to get it to keep moving. If we stop pulling, then it stops moving. And so a lot of people think that you have to apply a force to make something continue to move. But if you think about it for a minute, if we go into deep space, nowhere near any planets, like maybe 5 million light years away from a galaxy in the middle of nowhere, space, okay? And I take a baseball and I apply a force to it, the baseball is initially at rest in my hand. With respect to me, okay? It's at rest. I have to apply a force, but then I let go. The force has been applied, and the baseball accelerates from rest to some velocity that I throw it at. But after it's moving, that baseball will travel forever in a straight line throughout the universe. I do not have to keep pulling or pushing on that ball to get it to continue moving. You see, thousands of years ago, when scientists start really looking into motion, the common conception was that you have to keep pulling on stuff to get it to continue to move. But now that we know about space travel, you can see it in the space station all the time. If they throw an M&M or a candy across the room, the force is now gone. There is no force applied anymore, but that object is going to continue moving. So we're touching on Newton's laws, which we're going to get into in a minute, but you already know, it's not a big mystery. An object at rest tends to stay in rest, and an object in motion tends to stay in motion unless it's acted upon by an outside force. That means if I throw the baseball and it's moving, it will keep moving. I do not need to keep pulling on it or pushing to get it to continue moving. So forces don't cause, or forces are not required to maintain motion. That's the fallacy. That's what people don't totally get. Because when we pull on the carpet, it seems that way, but on the carpet it's different because there's a frictional force trying to slow it down. So when you're pulling on the carpet, the crate, you have to keep pulling to overcome the frictional force. But in space, there is no friction. Once you accelerate it and you let it go, it's going to keep going. So forces are not required to maintain motion. Forces cause a change in the motion. That means if the baseball is still, I apply a force, it accelerates from non-motion to motion, a change in its motion. If the object's already moving and I walk up to it or float up to it and start pushing on it, then the object will change its state of motion. It'll either speed up or slow down, or if I push sideways, it'll change its direction, which is also a change in motion. So forces only cause changes in motion. That's it. And what we call changes in motion, we have a word for that. We call it acceleration. Forces cause acceleration. That's it. They're not required to maintain motion once it's started or to maintain stillness once it's started. That happens automatically. Forces cause an object to change its state of motion. I'm saying it 10 times to drill it in. So now what we need to do is transition to talking about several types of forces, and then we'll talk about their components and how to break them down and add them in just a second. So probably the most common one that you talk about besides a push or a pull, the type of forces that we see in nature. Here's a baseball or something like this, right? We have what we call the gravitational force, and that acts in the downward direction. Notice I'm putting an arrow on top of every force because a force is a vector. It has a magnitude, a strength, along with some direction, and gravity acts downward. So this is called gravity force or gravitational force. So you can call it gravity force. Now, I need to stop and say that modern theories of gravity don't actually treat the force of gravity as an actual force. What we treat it as now, in terms of Einstein's theory, we treat gravity as a curvature of space and time, which we perceive to be a force. But that's kind of a subtle detail that we get to much later in more advanced physics. For now, we're just going to consider gravity to be a force, like a push or a pull, and the nature of why it happens is something that we learn about later, which we talk about curving space and time to make it happen and to pull it off later. But gravitational force, very important force. It's going to be almost every single problem. Another kind of force that we don't talk about too much until you get to physics is what we call the normal force. So if this is a block and this is the ground, of course gravity is going to act down on it, but what we don't talk about too much until you get to physics is there's actually an upward force from the table acting upward on the block. We put an N with a vector on there. This is a normal force. Normal just means it's perpendicular 90 degrees to whatever surface it's sitting on. This is called the normal force. Now you might say, I've never felt anything pushing up on me or as I'm standing on the ground, or how is it pushing? Was there hands in there? Is there hands pushing up? No, it's because of, we'll talk a little bit later about it, but basically whenever this thing sits on a table, it tries to microscopically bend the table, right? It's trying to push down on it. And the table is comprised of atoms and there's springiness there. Just like you pull a rubber band, it's going to want to pull back. If you push down on that table, it's going to want to push up because you're kind of like you're trying to bend the atoms and pull them apart, and their chemical bonds are causing a springiness to kind of try to get it to push in the upward direction, opposing the force of gravity, which is acting down. So anytime something is sitting on the surface, there's always a force pushing up. We're going to talk about it a whole lot later. It's called a normal force. In fact, even if the table is not horizontal like it is, if it's at some slanted angle, of course the thing is going to be sliding down, but maybe it won't. Maybe if you get it angled just right, it just barely hangs on there. There is a normal force that is acting perpendicular. It always acts perpendicular to the surface. All right, so we can draw a more complete picture of these blocks that we are pulling over here, which is the kind of thing that we talk about all the time in physics. Let's say we have the ground right here, and then we have some kind of block, some kind of long block here. And so what are the forces acting on this? Now we're going to talk about this a whole lot more later, but of course we have some force. I'm going to call it the pulling force, right? So that pulls it to the right. But we already said that this thing has a force of gravity on it, right? So I'll put this down here. This is a force of gravity acting up or acting down on the block, pulling it into the table. But we're going to talk about reaction forces later. There is a force that's being applied to the block from the table. That's called the normal force. And that's because, again, it's trying to bend the surface of whatever it's on, and that's causing a reaction force to push back up. There has to be a reaction force. We'll talk about Newton's laws and why it all happens, but that's essentially why. Because if you think of a rubber band, when you pull it, it tries to pull back on you. It's the same thing. You try to bend any surface, it's going to try to push back. That's the normal force. And so, of course, you have these forces acting in the vertical direction, and we're pulling it. But if we're on carpet or some kind of a surface that's not very slippery, then we have a frictional force we're going to talk about later. We'll call that lowercase f with a vector this way. Now, if you're not sure which way these are supposed to point, I mean, it's okay. We're going to get into it later. But if you know that if you pull something this way, the frictional force has to be acting opposite. I mean, you can't pull something and the friction push in the same direction as you're pulling on it. That would accelerate the thing even more. So, of course, the frictional force has to be in opposition to any force you're pulling on something or pushing on something. So if we're pulling this way, friction acts oppositely. So we're going to be drawing a lot of these diagrams to analyze situations here, but you can see that we have actually 4 different forces in here. All right, one more. Let's say that we have some block, and instead of a clean push or a pull like this, let's say I tie a rope to it, and this is going to be a terrible rope here, but this little thing is supposed to be a braided rope, right? And if I apply my force of a pull through the rope, then we say that there is a force in this rope, but we call it a tension, and we call it T. And this thing right here is rope. So lots of definitions that we have throughout all of these problems. It's all boiling down to definitions. You know, you have pushes and pulls. Those are forces. Anytime a force acts on an object, the only thing it can do is change the state of motion of that object. It tries to accelerate that object. We're going to learn about that a lot more when we get to Newton's laws, but there's the answer right there. You can solve most physics problems understanding that. We have a gravitational force acting down. We have a normal force from a surface acting up, even if the surface is at some angle. Because of that, we have lots of forces acting on objects when we push or pull them. And we have a new force, which we just call a tension, which is the force applied through a rope, which is acting on an object. Now, I've been dancing around this, and I haven't specifically said it, but what units do we use for forces in physics? Now, everybody has their ideas, you see. And some people use kilograms, right? But kilograms really is not a unit of force, really, it's a unit of mass. And when you have mass sitting in gravity, of course, gravity's pulling on it with some force. So it gets a little confusing. In the English system, we have the unit of pounds of force, which is a crazy unit. We never use that in physics. In physics, we learn and use the unit called the Newton. The Newton is the unit of force. We're going to talk a whole lot more about where the Newton comes from later, but I'll just tell you right now that I guess I don't even want to write it on the board. 1 Newton is about 1/4 of a pound if you like dealing with pounds. But if you don't want to talk about any unit at all, if you can picture a regular-sized apple, hold it in your hand, a good medium-sized, not too big, not too small, a good medium-sized apple, that's about a Newton. 1 Newton of force. And we use the abbreviation N, so 1 Newton, we just say 1 N. So in physics, it's always newtons, always. If you see kilograms, that is a mass. And we learn later how to change mass into a force of gravity, but the gravitational force is in newtons. Pushing and pulling are in newtons. Frictional forces are in newtons. Electric forces are in newtons. Magnetic forces are in newtons. You see the pattern. It's always newtons. Anytime it's a push or a pull of any kind, it's in newtons. So now what we need to do is talk about how these forces, when we have multiple forces, can apply and act on an object in order to get it to move. And what do we do when we have multiple forces? All right, so now we need to solve our first problem, but I encourage you to watch all the way to the end because I have several problems that kind of converge together for the main grand finale conclusion that I want you to get to. So please watch the whole thing. It's very important. First problem, it says Patrick is pushing a crate with a force of 10.0 newtons at an angle of 45.0 degrees below the horizontal. What are the horizontal and vertical components of the pushing force? So here is where the rubber meets the road. Here we have to really get into the math. It is not difficult, but we do have to do a lot of talking for the first problem. What we're going to learn is that, yes, of course, forces can act horizontally and vertically. Those are easy. But when forces act at angles, what we always do is split the force up into components. Remember, we talked about vector components a long time ago. I told you that any vector which has a direction can be broken up into a vertical direction and a horizontal direction of whatever it is the vector is that you're talking about. Here we're talking about a force. So we want to figure out if this person is pushing at an angle of 45 degrees, how much of the push exists in the vertical direction and how much of it exists in the horizontal direction. Let's find out. The very first step we always do is we always draw a picture. So if you're not good at drawing like me, that's okay. Just draw a rectangle. You're pushing a rectangle, fine. And it says that we have a 10 Newton force. How do you represent that? We represent that as an arrow acting like this. And what you do is you just label it F vector 10.0 newtons. This is the unit and it's acting at this direction. Now it also tells you that it's acting at a 45 degree angle below the horizontal. So if you can imagine an XY plane, then this would be horizontal. These would be positive angles, like positive 45, positive 90 degrees, and so on. But this is below the horizontal. That means, see how we have it drawn? It's acting down below. And it tells me what that angle actually is. So what you need to do is draw yourself a little dotted line to represent a kind of a horizon. And then you just tell yourself, you put a little angle in there, and you say that this is 45 degrees, right? Now, there's a lot of ways in which you can represent it. All right, it's a 45 degree angle down like this, or what you can do is you can put it on an XY plane like this, and this is X and this is Y, and what you can do, and you have freedom here, okay? You don't have to do it the same way. You can say, all right, this is below the horizontal, and remember, if these are positive angles, you can consider these to be negative angles, so you can say, this is negative 45 degrees. The negative sign tells you the angle is below the horizon. So you see how these two things are basically the same as far as the angle. If you take that arrow and put it down here, it's the same thing. So you can consider it being 45 degrees below the horizontal at an angle of negative 45, or you can consider it being a positive angle from measuring from, this is kind of like if it were measured from the negative x-axis over here. So you do have a little bit of artistic license in how you draw your pictures. If you write your angles as positive, you just got to be careful that the components come out correctly. I'm going to guide you through that as we go here. All right, I personally like to draw it more like this, to show myself that this is at an angle of negative 45 degrees here. But this is okay too, because this would be like a positive angle measuring up like from that negative axis there. So what do? Well, I want to teach you the right way instead of the hard way. So what we need to do is draw a picture of the components of this thing. If this guy is this vector right here, and if we say that this is like a 10 Newton arrow like this, then what I need to do is recognize that this vector can be split into horizontal and vertical components. So you can just draw your little triangle. It's the same triangle that is formed over here. Then you say that this is the force that exists in the horizontal direction, like an arrow that would be pointing this way. And then this is a vertical component of the force, which will be acting down. Do you see how, before we go any farther, that if I push horizontally and at the same time I push vertically down, then what's going to end up happening is they can combine together to behave the same way as a force angled in the angle direction here, because this angle right here is 45 degrees. So we're starting to get into how do you add these vectors together. Whenever you add vectors together or you break vectors apart, you basically have to consider a horizontal and a vertical component, and the directions of those components matter. If you're angling the force like this, then there has to be some horizontal component of the force, and there has to be some vertical component of the force. If you want to, you can think of this as just being directions. If you think about it instead of forces, just think about it as directions. Like, let's say I walk 10 meters at this angle. That could be the same thing as walking so many meters horizontally and then so many meters vertically down. I get to the same place. So this triangle here, it's representing forces, but it's broader than that. It represents any vector quantity. Displacements, which is when you walk certain directions, can also be represented, as you know, by triangles. And you all know that you can calculate the distance of a triangle, and so it behaves the same way with forces. All right, so let's move on. So if we're working with something like this, the way you do this is you say that this horizontal component f of x, or f sub x, is equal to the magnitude of the vector that you have, 10 newtons, I'm just going to write it as 10, times the cosine, because we're chopping in the x direction, so the cosine goes with the x direction, and the angle here, I've written it as 45 degrees, but since it's below the horizontal, the real angle, the actual angle, is negative 45 degrees. I need to put the negative in there to make sure that when I take the cosine in the calculator, I'm getting the right sign of the answer. All right? And so what you get here is 10, and what's the cosine of negative 45 degrees? The cosine of negative 45 degrees, if you think about the unit circle, the cosine is the projection onto the x-axis here, so you still get a positive square root of 2 over 2. And 10 divided by 2 is 5, so what you get is 5 times the square root of 2. And if you take 5 and multiply it by the square root of 2 in the calculator, what you're going to get is f sub x, 7.07 newtons. So this is the x component, 7.07 newtons. That means when you have something acting at 10 newtons at this angle, it's as if 7.07 newtons are actually pushing horizontally, and now we need to see how many newtons are acting in the vertical direction. All right, if you're not sure why I did it like this, just go back and look at the triangle. Well, I guess you can look at this triangle here, because sometimes we're not used to this in the beginning. You know that the cosine of any angle, what's the cosine of this angle? It's the adjacent side, f sub x, over its hypotenuse, but the hypotenuse is 10. So the cosine of the angle is adjacent over the hypotenuse. So if you multiply by 10, then we know that fx is 10 times the cosine of the angle, which is what I wrote here. But I don't really want you to write this. I want you to write it like this, because I want you to think about what you have is a total force of 10 newtons, and the cosine chops that force into the x direction to tell you the projection of how much of it exists in the x direction. So it's like 10 chopping into the x direction. This is how much is in the x direction. All right, so then what we need to do is let's go and do the same thing for the y direction. So if cosine chops in the x direction, what chops in the y direction? It is sine. So we have to take the total length of the vector, 10, and then we chop it down by the sine of what angle? Well, it's really 45, but since it's below, it's really negative 45, so we put negative 45 degrees. And then what we find out is the sine of a negative angle gives me a negative answer, and what you get is a negative square root of 2 over 2. And so what you get is, this is 10 divided by 2 is 5, but the negative sign means you have negative 5 times the square root of 2. And so what you have here is negative 7.07 newtons. And this is the vertical component of that force. Now, there's a lot of stuff I want to talk about here, because this is where I've gotten hundreds and hundreds and hundreds, literally hundreds of people saying, how can this be? And so I want to spend a minute to really make sure you understand. So even if you think you do, please devote the next 5 minutes to making sure that you do, because it absolutely affects every problem we solve from here on out. What we are saying is that when you have a force of 10 newtons acting downward at a 45-degree angle, what it means is it behaves the same as 7 newtons, 7.07 to be exact, acting in the horizontal direction, this side of the triangle, acting horizontally, right? And what we say is that the vertical is also negative 7.07 acting in the vertical direction like this. Now, the reason they come out to be the same is because the angle was exactly 45 degrees, all right? One thing that we write a lot in physics is we can say that these are two kind of like vectors that could be added together. You can see there's arrows here. So what we can sort of say is that the total vector was really the x vector plus the y vector, because the x vector acts horizontally, the y vector acts vertically, but we can say that we add them together and we get the total force. This is where people kind of bake their noodles here, right? Because it looks like you have 7.07, and if you add it to this, negative 7.07, it looks like the answer is 0. And if I change the problem, which in a previous video when I had a different problem, if I changed it to where it was a positive 45 degrees, instead of it being a positive 45 degrees, what if the force was going up like this at an angle of positive 45 degrees at 10 newtons right here? right? Then everything's the same. The positive 45 is going to give you the same thing here. The positive 45, when you take the sign, is going to give you the same number with a positive sign. So this, in that case, would be 7.07 newtons. And then this side also would be 7.07 newtons. If I change the angle, I just get the same signs right here. You see, this looks impossible to a lot of people when you talk about forces, because people think that when you have two forces that can be acting, then you basically add them together. But you can see that 7 plus 7, that's already 14 newtons. 7.07 plus 7.07, as I've written it right here, like you're adding them, then it looks like 14.14 newtons. And that's bigger than the 10 newtons I started with. So for years, people have been like, well, you can't do that because when you add these forces, it's bigger than the force you start with. But your understanding is flawed, okay? Because here is how this actually works. These are not numbers you are adding together. They are not numbers. They are vectors, right? So yes, of course, if I have two vectors where literally one person pushes with some amount of forces, like, 5 newtons or something like this, and then a second person is pushing on the first person with additional 5 newtons. So they're literally pushing a block in the same direction, like one after the other, and they're both pushing with 5 plus 5. Then of course, 5 plus 5 is, going to give you a 10 newtons. Because they're acting in exactly the same direction. Of course, then yes, you add them up, right? But what if I had one person, like a block in the middle, right? What if I had one person acting with 5 newtons that way, and another person pointing like this with 5 newtons this way? It's really like 5 newtons like this and 5 newtons like this. So you can consider this one to be almost like negative 5 newtons because it's acting in the other way. Well, so I'll put a little negative sign there to remind you that it's basically going the other way. So yes, when you add these guys together, this block is not going to move at all because 5 newtons this way, 5 newtons this way, they cancel each other out. Really, it's because you subtract them, right? So you can see when the forces are exactly lined up, of course you can add them. But if they're lined up the other way, you're still adding them. But because one is negative, you're really subtracting them. And so the block doesn't move. So you start to think that any two forces you apply to an object, you just add them. But see, these cases are only because the forces are lined up. But if you consider a block that is acted upon by a horizontal force and a vertical force, you don't just add the numbers. 7 plus 7 is over 14. It's 14.14 newtons. The reason why it becomes higher than 10 is because you can't just add the numbers like that. You have to add them using trigonometry, taking into account the angles that you have there, because these things are not acting they're not acting in the same horizontal or vertical direction, right? Clearly, you can add them here and here, but that's only because they're lined up. In fact, here you're adding them, here you're sort of subtracting them. So clearly, there's something different going on when you start bending this thing around to go in the other direction. So here's an intermediate state where they're not fighting each other, and they're not this. It's like you're halfway to the other side. And of course, you use trigonometry in the Pythagorean theorem and in the trigonometry to get the answers here. We're going to do more with this as we move through this lesson, but I wanted to get that out in the open before. It is okay that this is, in this case here, 7.07. This is also 7.07. It is okay that the answer is bigger than 10 because these are not lined up. This one is pushing it horizontally. This one is pushing it vertically. They act together to behave the same as if a single force acts at a 10 newtons at this angle. If you have two situations, one with two forces and another with a single force, the block will move the same. That is the punchline. That's why they're equivalent. And that's kind of the punchline of vector addition. But notice in our actual problem we had, one of these is positive and one of these is negative. This negative one just means that the y force is acting down, right? It's acting down. And this one is acting horizontally, and together they combine to produce a force that acts down and to the right like this. So that's why one of them is negative in our problem. All right, so now I want to transition. We're going to use this. We're going to use this in a subsequent part of this lesson. But for now, just hold it in your back pocket, and I want to change to a different situation. Here, I gave you a force at an angle, and I said, tell me the components. We used trig to find the x component and the y component, and I did a lot of talking to show you why it was okay. But now we're going to go reverse. Instead of doing this, what we're going to do next is I'm going to give you a box, and I'm going to apply two forces to this box. What forces should I apply? Well, here we have a force. I'm going to act up, and a slightly longer forces, I'm going to act horizontally. Notice these forces are acting at the exact same point. So it's like one person pushing like this, one person underneath like pushing up, and they're pushing on exactly the same corner of the box. Now this force, I'm going to call it 4 newtons, and this force, I'm going to call it 3 newtons. So we're pushing more in the horizontal direction, or person number 1 is pushing more this way. Person number 2 is also pushing, but with less force in the up direction. Now, before we do anything else, what do you think is going to happen to this box? Like, if I literally took a box and literally could do this, one person pushing horizontally, one person pushing up, neglect gravity, pretend gravity's not here, we're doing this in deep space. Then this force acts to push the box horizontally. This force separately and independently acts to move the blocks vertically. So what's going to happen after some period of time is basically the box is going to be in a new position over here, right? It's going to move in some angled oblique direction, right? Because this force is going to move it this way, and this force is going to move it up. So it's going to move in some angled direction, right? So how do we actually figure out how these two forces conspire and add together properly to add these vectors together to figure out what happens? Well, we do vector addition. And remember, vector addition, we put head to tail of the vectors. And so what we do, we can just add these vectors. We can add these vectors together. So the way we add vectors, you see how the two arrowheads, because they're acting at the same point, they're right on top of each other. We don't add them like that. What we do is we put them head to tail. So we put the 4 Newton vector like this, and the other vector, we can take this 3 vector and we can move it around anywhere we want as long as it keeps its orientation, and we put the tail of it connected to the head of this one. So this was 4 newtons, and this is 3 newtons. This is how we add vectors. We can slide them around. We just put them head to tail. And then to figure out what we call the resultant of these two vectors, or what we do when we add them together, we call it the resultant. What we do is we connect the starting point to the finish point of the other arrowhead. So this red one here, this is called the resultant. We call it F sub r, and I'm going to call that resultant vector. So my question to you is, we know that if we have two forces acting, then of course we can apply a single force horizontally and a single force vertically, and the block will move at an angle. But let's just try to figure out, what would a single force look like? Instead of two forces, what is the single force acting at an angle that would make this block move the same exact way? That would be what we call the equivalent vector to these two, also called the resultant vector, also called the vector addition of these vectors. We have to add them. You know, we add numbers. We know that 3 apples plus 4 apples is 7 apples. Those are like equivalent things because they're just numbers. But we can add vectors in a similar way. We can figure out what this vector is that will make the block move in the same way that these two vectors make it move. But notice that this forms a right triangle. Every time you do this, it forms a right triangle like this because one was horizontal and one was vertical. So to figure out that resultant vector, what you do is you take the square root of 3 squared plus 4 squared, or 4 squared plus 3 squared, however you want to do it. 4 squared plus 3 squared. This is the Pythagorean theorem. C squared is a squared plus b squared, and then we have to take the square root of both sides to get this by itself. And what you get is the square root. 4 squared is 16, 3 squared is 9, so what you get is the square root of 25, and when you take the square root of 25, the resultant vector is 5 newtons. 5 newtons. Right? Now, this immediately throws people for a loop because they say 3 plus 4 is 7. How can the resultant be 5? Just calm down for a second. Just hold on, and we're going to get there and we're going to talk about it. But it's the same reason as before, because you don't add vectors by just adding numbers. I just showed you how, if you add numbers together, 5 plus 5 is 10, but yet this is like 5 minus 5. So it's addition, it's subtraction. It behaves differently in different situations depending on the angles and how everything is the directions of things. That's equally important. So this is what we call the resultant vector. Now, what is this angle here? Because there is some angle here. How do I find that angle? Well, I can say that the angle is going to be equal to the inverse tangent, because remember, the inverse tangent, or the tangent function, is y over x, or opposite over adjacent. So 3/4. So the inverse, so I can say tangent of the angle is equal to 3/4, so I take the inverse tangent to both sides. And if I put 3 fourths in the calculator, that's 0.75. Take the inverse tangent in degree mode, I'll get 36.9 degrees. So what we are saying is that if I take a block and I apply 2 different forces, one at 3 newtons going up, one at 4 newtons going to the right, then we know that this block is going to move obliquely, right? And what we're saying is that that situation with 2 forces acting is exactly equivalent to a different situation where a single force of 5 newtons acts at an angle of 36.9 degrees. So let me make sure you totally understand what I'm basically saying here. So this is situation number 1. We have a 3 Newton force, and then horizontally a slightly longer arrow, 4 Newton force. What we're saying is that that is situation number 1. Situation number 2 is where we're basically saying that we have a single force, instead of 2 force, a single force of 5 newtons, and the angle that this thing acts is, if I draw a little horizontal right here, 36.9 degrees. 36.9 degrees from the local horizontal acting up into that block right there. This thing is going to make the block move at some angle. These separate forces are going to make the block move in exactly the same angle. So if you just had if you could just see the block, and you didn't know if it was the 2 forces acting, and you observe the motion of the block, and then you do it again, and somebody else changes it to the single force acting at that angle, moving the block will move the same, because these are 2 equivalent situations. And we say that the vector addition of the horizontal, the same thing I wrote here, the vector addition of the x direction plus the y direction force gives me the resultant vector. But here's where it trips people up. This is not a plus sign between numbers. This is not numbers, okay? Because, of course, 3 plus 4 is 7. So people think, oh, well, there's got to be 7 newtons acting on the block. Well, sure, but they're in different directions. So because they're in different directions, the aggregate motion of the thing is not like 7 newtons acting in one direction, because one of those forces is acting up. That one is acting only to move the block up. The other force is acting horizontally, which is only pushing the thing horizontally. So it's not 7 newtons acting at some angle, because those forces are not even in the same direction. How do you handle it? You add them using vectors. You find an equivalent vector using the Pythagorean theorem. That tells you the magnitude of the resulting vector. And then you find the angle from trig, and then this situation right here moves the block exactly the same as this. I've literally gotten hundreds and hundreds of people telling me that this is wrong. It's not wrong. It's just that you don't have everyday experience with adding forces like this. So it seems like it's violating something, but it's not. If you want to replace these, this triangle, if you want to replace this with something else to make yourself more comfortable, fine, let's do it. Let's say you walk 4 kilometers east, followed by 3 kilometers north. You land here. Now let's say you start over again and you walk. Do you think you're going to walk 7 kilometers? Do you think this distance is 7 kilometers? No, it's 5 kilometers. That's the Pythagorean theorem, 5 kilometers at an angle of 36.9 degrees. All right, if you want to change it again, let's talk about the velocity of the wind. Let's say from this starting point, there's wind pushing at 4 meters per second this way. And then there's also some north wind pushing 3 meters per second north. Then the equivalent wind would be a wind acting at 5 meters per second, but at an angle. And any object you put in the wind stream is going to move the same when acted upon by those 2 different situations. That is absolutely critical. So what we can say is that the resultant vector is equal to the x vector plus whatever that y vector is. But this is not the same. It's 3 plus 4 is 5. This is not any problem here, right? Because people say, oh, 7 is different than 5. Well, I'm trying to tell you, when you add vectors like this, you have to find the length of the new vector with the Pythagorean theorem, and you have to find the angle using the inverse tangent or some other trig function. All right, so what we want to do now is we have 2 different situations. I have a block acted upon by these 2 forces, and then I have another situation where I had a block acted upon by this single force, which we resolved down into 2 totally different forces. Now what I want to do is talk to you about something extremely important. What happens when we have a block or some object acted upon by 2 totally different forces acting at different random angles? How do you think you handle it? Well, I'll tell you the roadmap. We take force number 1, we break it into horizontal and vertical components of the force. We take force number 2. We break it into vertical and horizontal components of that force. And because the horizontal ones are acting in the same direction, we can just add them. See, we can add forces as long as they're in the same direction. And the horizontal ones will be in the same direction. The vertical ones, we can add separately because they are in the vertical direction and they're lined up. So we can, of course, add them when they're lined up. Then, when we have those additions finished, we have the components, x and y, of the resultant force. So when we add forces together, two different oblique forces, we break them into components and add them. And that's how we get the answer. So let's say we have a new situation, right, with a block. It's always a block, right? And the first situation is I'm going to have, I'll try to draw this one a little bit longer, a 10 Newton force. So I'll put 10 newtons. And this angle, even though I drew it too shallow, this is an angle of 45 degrees. This is the exact situation we had in the beginning. We had a 10 Newton force, 45-degree angle acting downward, down and at that angle. Same here. I've just not drawn the thing quite perfect. And let's say acting on exactly the same object. How do I want to draw this? Draw it like this, I guess. Not so long. Like this. Something more like this. Another arrowhead acting at the same exact place. And this one is 5 newtons. And the angle here is, I'll do 36.9 degrees. Now this angled force right here at 36.9 degrees, this is what it worked out to be a minute ago. Because what we had here is, where are we at here? Yeah, this is exactly the same thing. So I drew it kind of at the corner down here, so I'm kind of moving it up to this corner. 5 newtons, 36.9 degrees acting up. 5 newtons, 36.9 degrees acting up. And exactly the same point, I have this vector that we used in part A coming down. How is this block going to behave? That's what we want to figure out. Well, it's going to be impossible to do without using components, right? We're not human calculators. So what we do is we break this force into its vertical component and horizontal component. We use this, break it into its vertical component acting up, horizontal component acting to the right, and then we add the components together. So what we say is force 1, which is the 10 Newton force acting at that angle. We already know what the answer is. The 10 Newton force acting at the angle is in the x direction 7.07, in the y direction negative 7.07. That's why I chose it this way. So let's switch colors. And I'll say Fx is 7.07 newtons and Fy negative 7.07 newtons. Okay? And then the next thing we do is we say, what is force 2? And that's the 5 Newton force that was acting on that angle. Now, what did that resolve to? So when it was the 5 Newton force, that formed a 3, 4, 5 triangle, right? That's why I picked it, because 3, 4, 5 we know is one of the Pythagorean triples. And so it forms a right triangle. So what we said, when we have 5 newtons acting at this angle, the horizontal one is 4 and the vertical one is positive 3. So what we then know is that this force resolves. So the x direction is 4 newtons and the y direction is 3 newtons. So we have the forces broken down into their respective components. What do we do now? What we do now is we add them together. But we don't just add the raw vectors, like this. We add the components of the vectors. So what we say is we say that the force, which is what we call the net force, acting in the x direction, when we add the x components, it's this plus this, which is 7.07 plus 4, and this is, of course, in newtons. And so F net in the x direction is 11.07 newtons. So this is 11.07 newtons. Then we do the exact same thing in the y direction. What we say is the force, which is the net force, when we add them together in the y direction, is its y component, negative 7.07, and then we add this y component, 3. And so the net in the y direction, negative 7.07 plus 3 gives you negative 4.07 newtons. Now let me just stop for a second and just think for a minute. The original two forces, one was acting down, one was acting up, but they were still acting horizontally to the right. So its horizontal component was a positive number acting to the right. This one's horizontal component was acting also to the right. So we add them, we get a bigger number acting to the right. So this is like having two forces ramming it this way, and of course the new resultant force has a bigger component in the x direction because the components have now acted in the x direction together, giving you a bigger component in the x direction. But look in the y direction. This one's acting down, and this one's acting up in the y direction. So they're fighting each other in the y direction. One of them was negative because it was acting down. The other one's positive, acting up, and they end up subtracting each other to give you a smaller number, than just adding them, I guess is what I'm trying to say, because it's like 3 minus this to give you -4, and that's basically still acting downward, but not as much as it was before. Notice the first force was acting downward with this amount of newtons, but since they're fighting each other, the resultant is acting downward with a fewer amount of newtons. So on a component by component level, layer, they're adding and subtracting like you would expect, and because one is down and one is up, they're fighting each other, and so the resultant is a smaller downward guy there. So then, now we have these components. How do we turn it back into a single vector? Well, first, let's just draw a little picture. The x force here is 11.07 newtons. That's a positive number acting to the right. This one is a negative 4.07 newtons. You have to angle it down because it's a negative number here. And so what is that resultant force going to look like? It's going to be going from the tip to the head right here. What is this? What is F sub r of the resultant vector of when you add these guys together? So now we have to use the Pythagorean theorem, because this, remember, you can't just add them. You're adding forces. You have to figure out the length of this triangle to figure out what's the equivalent force to these two acting in the horizontal and vertical direction. And so what you say is F sub r. I need to put absolute value, telling you it's just the length, not the direction of the resultant vector. It's the square root of these two things squared. So 11.07 squared plus, and inside here, negative 4.07 squared. And before I do anything else, let me go back here. Where did I do it? Let me go back here. Yeah, so when I put the resultant vector is equal to this, Pythagoras, I was a little sloppy. Really, you should put the absolute value of the resultant. It's just the length is equal to the square root of the squares of these things. So the length of the resultant vector is equal to the 5 newtons at this angle. That's the way you should write that. All right, so what you get here is 11.07 squared works out to 122.5. And then the negative 4.07 squared works out to 16.6. You still have to take the square root after you add those guys together. So what you do is you add these guys together, then you take the square root, and you get 11.8 newtons. I'm going to circle this. And so this is the equivalent force acting on that block. And what would be the angle? So the angle would be the inverse tangent of y over x. It's always y over x. So if this is the angle right here, which is what we want to find, the tangent of this is opposite over adjacent. So it's y over x. So negative 4.07, and then you have 11.07. All right? And what you get here is the inverse. This is the inverse tangent. When you take negative 4.07 and divide by 11.07, you get negative 0.37. And when you take the inverse tangent of that negative number, what you get is negative 20.2. Negative 20.2 degrees. What does that mean? That means that it's acting below the horizontal. So this is negative 20.2 degrees. And this guy, FR, the resultant is 11.8 newtons. So what we are trying to say is, if you had a block like this, acted upon by two oblique forces, one of them is 10 newtons acting at a downward angle, which the angle is defined here. One of them is 5 newtons acting at an upward angle. This situation is going to move the block. And it's going to move the block. Just look at how it's set up. You have a larger force acting down than the 5 Newton force acting up. So we expect the block to move and slide, if it's in space, kind of this direction. We expect it to move down when acted upon by those two forces. What we're saying is it behaves exactly the same as a force of 11.8 newtons acting at an angle of 20 degrees down below the horizontal. And look at the direction of this line. It's sliding the block. If the block were actually here, it would be sliding it down in the direction that we would predict by looking there. So how did we do it? we took a look at the first force, we split it into components. We already had the components from a previous problem. We took this force, we split it into components. We already had the components because it's a 3, 4, 5 triangle from a previous problem. Once you have the forces in components, then you can add, literally algebraically add the x forces together, and we get a new x component resultant force. We add the y forces together, and we get a new y component force. When the x forces are lined up, of course, the force gets bigger. The y forces in this case were in opposition, so they ended up subtracting from each other, but in any case, we get a new x and a new y force. Then we do the same business on that. We turn that back into a single vector by using the Pythagorean theorem, the square root of the squares of each of the components. And then that gives us the magnitude of the resultant force. The angle comes from the inverse tangent of y over x. So drawing these pictures is critical. I highly, highly recommend that you draw these pictures because the signs are going to matter. And so I'm going to close this whole lesson out by writing a couple of things down, which I could have written in the beginning, but would have confused everybody. And now I don't think they're going to confuse anybody after we have done this. What we generally say in physics is that if you want to find the resultant force, right, what you do when you have a body acted upon by multiple forces, then what you do is you take that first force, which is a vector, and you add that to some second force, which is a vector, and you add that to some third force, which whatever the third force is, which is a vector, and however many forces you have, if you have 10 forces, you can add them all together. 20 forces, you add them all together, and you can replace all 20 forces acting on the object as if they were a single force acting on the object. And that is how we solve problems. Because if you have a problem in real life, like a rocket, and it's acted upon by lots of forces, 5 engines at the bottom, slight different angles. Okay, there's wind forces, there's gravity forces, it's bending over, there's structural forces, there's maybe forces of radiation from the sun, there's forces everywhere. How do you do it? Well, you add the forces together. But when we write an equation like this, it's not just adding numbers because there's vector arrows on all of these. This means to actually add them together. What we really have to do is take every force and break it into horizontal and vertical components. We add the horizontal components, we get an answer for the horizontal component of the answer. We add the vertical components. We get an answer for the vertical component of the answer. That's the answer in the component form. Then we turn it back into a single vector if we want to. So what we can say then is this is true. The resultant vector is the addition of all the individual vectors. But we can say in terms of components that the resultant vector or the resultant force that exists only in the x direction is the sum of the forces that the components in the x direction. And we can say that the resultant vector in the y direction is basically going to be equal to the sum of the components of the forces in the y direction. This is just saying that we add the x components to get the x component of the answer. We add the y components to get the y component of the answer. That's all it's saying. So this is the vector form, and this is kind of the component form of adding vectors together. I highly recommend you watch this video a couple of times. I could have broken this video up. Of course I could have. But the problem with that is that you lose sight of why we're doing it. If I just have one lesson on breaking components and another lesson on adding and another lesson on this, then you lose the big picture of how do we do it. So yes, it makes it longer, and I'm sorry. Sometimes you have to sit through something to get the big picture. Watch it a few times. If you're a little rusty on how do you do all this trig, then please stop and go review your trig. Because I have to assume you know that, and I have reviewed it already with you anyway, but I have to assume it, otherwise we'll never get anywhere. So if you're looking at the sines and cosines and you're like, I have no idea what he's talking about, then go back and review my trig lessons and also the lessons in physics that review this stuff. All right, please watch this a couple times. When you feel like you understand what a force is, how it acts, how to handle multiple forces, follow me on to the next lesson. We're going to continue building your skills solving problems.
Learn anything at mathandscience.com.